Good morning to all. I am PM Chillapandi, Assistant Professor from Department of Mathematics. I have been working as an Assistant Professor in SNS College of Technology, Coimbatore. Today I am going to present you a case study on the title Application of Fourier Transform. Let us see what is inside of this case study. As we know that Taylor series representation of a functions are valid only for those functions which are continuous and differentiable, but there are many discontinuous periodic functions which require to express in terms of an infinite series containing sine and cosine terms. Fourier series, which is an infinite series representation of such functions in terms of sine and cosine terms, is useful here. Thus, Fourier series are in certain sense more universal than Taylor series as it applies to all continuous periodic functions and also to the functions which are discontinuous in their values and derivatives. Fourier series a very powerful method to solve ordinary and partial differential equation, particularly with periodic function appearing in as non-homogeneous terms. Here you can see a wave. I just explain what is this. You just take a spring, okay? You just press that, you give a force to that spring, then you can see like this atmosphere. The spring will spring, okay? So from this I am going to apply my Fourier series and I am going to explain my Fourier series from this example. Consider a mass spring system as before where we have a mass on M on a spring with spring. Constant K with damping C and a force f of t applied to the mass. Suppose the forcing function f of t is 2L periodic for some L greater than 0. The equation that governs this particular setup is mx double dash of t plus cx dash of t plus kx of t is equal to f of t. The general solution consists of the complementary solution xc, which solves the associated homogeneous equation mx double dash plus cx dash plus kx is equal to 0, and a particular solution of one we call xp. Okay. For c greater than 0, the complementary solution xc will decay as time goes by. Therefore, we are mostly interested in a particular solution xp that does not decay and is periodic with the same period as f of t. We call this particular solution the steady periodic solution and we write it as xsp as before. What will be new in this section is that is consider an arbitrary forcing function f of t instead of a simple cosine. For simplicity, let us suppose that c is equal to 0. The problem with c greater than 0 is very similar. The equation is mx double dash plus kx is equal to 0 has the general solution x of t is equal to a cos omega t plus b sin omega t, where omega naught is equal to root of L divided by m. Any solution to mx double dash of t plus kx of t is equal to f of t is of the form a cos omega t plus b sin omega t plus xsp. The steady periodic solution xsp has the same period as f of t. In the spirit of the last section and idea of undermined cosines, we first write capital F of t is equal to C naught divided by 2 plus summation n is equal to 1 to infinity Cn cos n pi divided by L t plus dn sin n pi divided by L t. Then we write a proposed steady periodic section x as x of t is equal to a naught divided by t plus summation n is equal to 1 to infinity a n cos nx divided by L into t plus bn sin nx divided by L into t, where an and bn are unknowns. We plug x into the differential equation and solve for an and bn in terms of cn and then dn. Now we are going to apply our Fourier series in heat equation. Heat on a insulated wire. Let us first study the heat equation. Suppose that we have a wire or a thin metal rod of length L that is insulated except at the end points. Let x denote the position along the wire and let t denote the time. See the figure now. Here we have a object. We are going to heat this object, okay, at the origin. The heat is insulating to that material. Then now we are going to apply Fourier series concept in this process. Let us u of x comma t denote the temperature at point x and time t. The equation governing this setup is the so-called one-dimensional heat equation, that is dou u divided by dou t is equal to k times dou square u divided by dou x square, where k is equal to del q divided by a del t and x divided by del t, where k greater than 0 is a constant. The thermal conductivity of the material, that is the change in heat at a specific point, is proportional to the second derivative of the heat along the wire. This makes sense if at a fixed t the graph of the heat distribution has a maximum, the graph is concave down, then heat flows away from the maximum and vice versa. We will generally use a more convenient notation for partial derivatives. We will write u1 instead of dou u by dou t, and we will write u double x instead of dou square u divided by dou x square. With this notation, the heat equation becomes ut is equal to k times u double x. For the heat equation, we must also have some boundary conditions. We assume that the ends of the wire are either exposed and touching some body of constant heat, or the ends are insulated. For example, if the ends of the wire are kept at temperature 0, then we must have the conditions, that is u of 0 comma t is equal to 0, then u of x comma t is equal to 0. Thank you. I hope you can have a clear idea about my case study. Thank you so much.